So let us continue with measuring earthquakes. So will any one of you say me that
We had an earth.
yesterday what all vocabulary terms we studied in measuring earthquake? How can you measure earthquake? With what is the device? What is the device used to measure earthquake? I have shown you here, I have spoke about it. Any one of you. It starts with S. Yes, Noor, how can you measure earthquake? With what device?
Seismometer.
Yes, okay, seismometer. It is called as seismometer, S-E-I-S, mometer, correct? And if I want to take a reading, you know, the PQR wave, Judy, what is it called as? It's called as seismogram. It's, you know, where you get that PQR reading, you know, that goes up and down, like how it happens with our ECG of heart. And then next we have time and distance graph. We have time distance graph. Okay, so the tool which was used as seismometer, and the later on the readings how they take is in seismogram or time distance graph. Very good. This is what we have learned in yesterday's class. So today we are going to see with and we studied about focus again. We studied about epicenter and those, you know, seismic waves, what are around the epicenter and focus. And today we are going to learn about magnitude. We are going to learn about magnitude.
That take place during an earthquake. See if you can match these key terms with the images. Drag each label to the proper image.
This we have done in yesterday's class. It will be like revision. I want you to tell me where is the focus, where is epicenter, where is the surface wave, and where is P wave and S wave. Let me start. Zishan, can you tell me where is the surface wave? Which picture is the surface wave?
The third one.
Wave. When I talk wave, where do you see wave? Which picture do you see wave? Surface.
Oh, the first one.
Hmm? First one, yes. Now, what's your name? Judy, can you tell me which is epicenter and which is focus?
Focus is the third one.
The third one is the focus. It begins, and epicenter is above the focus. That is very good. And Noor, can you say me which is S wave and which is P wave? S wave and P wave.
S wave is the last one.
Very good. And the P wave is excellent.
Great job. The focus.
I don't know why is she.
A seismometer is a tool used to measure the movement of the ground, particularly during.
This was the seismometer, okay, where they put it in the ground and that it measures the movement of the ground during an earthquake. This is a device where it checks the movement or where it records the movement of the ground during an earthquake, okay?
Okay.
Seismologists use three.
Again, seismologist is a person who's studying all of this. So we are using seismograms, we have travel time graph data, we have epicenter in the map, and we have finding the epicenter. This is what we have learned, but I am revising again and again so that you understand it more clearly.
You've learned a lot about how seismologists find the epicenter of an earthquake. The time between the arrival of the P waves and S waves is called lag time. Seismologists use the
every waves what they study, even if it's study of my heart, and they are saying the sound, you know, the loved up sound or PQRS wave, they have from P to Q, there is some time. I know it's milliseconds, it's millisecond, girls. Okay, the time my heart pumps and then get back to the normal position. Like that, there is, in milliseconds, the whole world changes with an earthquake. There is a time. There is from between to P to Q, there is 120-second lag time. We call it as lag time. Then from P to S, okay, P to S, and again when S starts, and then again P begins. So that they have given 120-second lag time, 170-second lag time, 200-second lag time, and 150-second lag time.
Lag time to determine how far the seismometer is from the epicenter. The seismogram showing the shortest lag time was made closest to the earthquake. Which seismogram was made closest to the epicenter of the earthquake? Click on your answer.
I'm sorry. We will first click and then we'll do it.
The amount of...
1 second.
You've learned a lot about how seismologists find the epicenter of an earthquake. The time between the arrival of the P waves and S waves is called lag time. Seismologists use the lag time to determine how far the seismometer is from the epicenter. The seismogram showing the shortest lag time was made closest to the earthquake.
See, listen to me. P wave means still the waves have not started, okay? Means the earth is not shaking. If there is so much time between P and S, that means 200 seconds. This is the most. That means the earthquake is not that shaky. So the less time, that means less time is more danger one. So what is the question asked? Which seismogram was made closest to the epicenter of the earthquake? Which is closest to the epicenter? Let us see 120.
That's right.
Okay.
St. Louis has the shortest lag time. The S wave arrived...
That the shortest time, that means the wave started very quickly and that is very near to the epicenter. So that's why I chose the shortest lag time.
The amount of energy released during an earthquake is called its magnitude. The Richter scale, developed in 1935,
When it shakes, it releases energy. More energy, more is a magnitude. Okay? In like when it is 5.0, maybe it occurred in Jeddah also. Maybe many times and we cannot feel it. Because 5.0 is like, we can see the windows breaking, not windows breaking, actually 5 also we have not felt. We never felt at our place, but maybe 3.4 or 4.2. So windows can shake and they can have cracks with this kind of earthquake.
Rates an earthquake's magnitude based on its seismic waves. The moment magnitude scale is a newer scale that rates an earthquake's magnitude based on the amount of movement there is at a fault, the area of the fault surface that moved, and the strength of the rock. Both scales use the same numbers to indicate magnitude. The Richter scale is no longer used to measure earthquake magnitude because it is inaccurate.
They say that it was before the Richter scale, but now they're not using this Richter scale because it's not that accurate. And you all know very well that now everything is so, organized and everything is, with the machines. So they're not using those, what do you call it, as manual scales. Hello girls, can you hear me? Hello?
Yes.
Yeah, they're not using manual scales. They're using the machinery scales.
For larger earthquakes, moment magnitude is the preferred scale that scientists use today. Click the images to learn more about magnitude. You might not notice an earthquake with a magnitude of 4.0, even if you were at its epicenter. But you would definitely notice an earthquake with a magnitude.
They say if the magnitude is 4, even if I'm sitting above the epicenter, like, where I'm sitting underground, there the epicenter starts shaking, but I will not feel because that 4 magnitude is very less. With 5, we might feel the ground moving and see windows breaking. We can see the windows breaking.
Of 5.0. For every 1.0 increase on the magnitude scale, the amplitude of the seismic waves is 10 times greater.
Wow, 10.
You are much more likely to feel the ground move in a 5.0 earthquake than in a 4.0 earthquake. For every 1.0 increase in magnitude, an earthquake releases 32 times more energy. To compare a magnitude 6.0 to a magnitude 4.0 earthquake, multiply 32 by 32. A 6.0 earthquake releases
Whoa.
1,024 times more energy
More
than a
energy.
4.0 earthquake.
So much.
In 6.0 earthquakes, pictures might fall off the wall and furniture might slide.
In 6, they say the furniture might slide, but nothing, the building cannot break in 6. Now see, when I talk about 7, it's like 1024 times 32. That will be so much.
An earthquake with a magnitude of 7.0 releases 32 times more energy than a 6.0 earthquake. In an area near the epicenter, ground movement would be much greater than in a magnitude 6.0 earthquake. During an earthquake with a magnitude of 7.0, many buildings might be badly damaged. On average, there is only one earthquake with a magnitude of 8.0 or higher every year in the entire world. An earthquake with a magnitude of 8.0 is extremely dangerous. It is likely to cause buildings and bridges to collapse. An earthquake with a magnitude of 9.0 releases more than 1 trillion times more energy than a 1.0 earthquake. In 2004, an earthquake with a magnitude of 9.1 struck the Indian Ocean. This quake caused a tsunami, or large sea wave, that killed more than 200,000 people. Intensity describes the amount of damage caused by an earthquake. The modified Mercalli intensity scale is used to describe the intensity of an earthquake.
So that scale, which was previously with the scientists, it is no more used. But now they are using modified Mercalli intensity scale, which they have shown here, and we'll see about it.
Quake. It is not a mathematical scale. Instead, it is based on observed effects. An earthquake's intensity is different in different locations. Click the dots on the line to. This is the modified Mercalli intensity scale. The lower numbers indicate very little damage. For example, few people would even be aware of a level 1 or 2 earthquake. The higher numbers indicate greater damage. Even well-designed buildings may be damaged during a level 9 earthquake. Seismologists use a shake map to show the intensity of an earthquake. Notice that the intensity indicated by color drops as you get farther from the epicenter of the earthquake.
With this map, they have shown us, like, you cannot feel, you cannot lightly, you can feel, and then it's moderate, strong, very strong, severe, violent, and extreme. And they have also shown you the, the peak and all of the readings.
For example, the epicenter is marked by a star on the map above the table. People who experience an earthquake with an intensity rating of 2 or 3 are likely to notice the shaking, especially if
they don't even notice with level 2 and 3, they don't even notice the shake of the earthquake.
They are near the tops of tall buildings. However, there will be little or no damage. A level 6 earthquake is likely to cause windows to crack and objects to fall off shelves.
When I say level 6, you can remember the magnitude 5. Because in the magnitude 5, they say that the windows will shake.
However, well-built buildings should not suffer structural damage. At level 10 or higher, bridges and buildings will be damaged.
So that means level 10 is like magnitude 8 and magnitude 9. Even 7, they told us that the building might fall, especially the areas near the epicenter.
The moment magnitude scale is many factors affect how much damage an earthquake will cause. Magnitude and distance from the epicenter.
Girls, of course, the magnitude is nearby the epicenter. The magnitude and the distance from the epicenter definitely affect the amount of damage.
Centers certainly affect the amount of damage. but so do the local geology and the size of the population. Click the images to learn more. Magnitude is a measure of the amount of energy released by an earthquake. Earthquakes with a higher magnitude cause the ground to move more.
Just now I told you girls. Now let me ask Zishan, what will be the magnitude? What is the number which you will say it is higher magnitude and there's a lot of destruction? Yes, Judy, what magnitude do you think that it will be very higher? Yes, Noor?
Earthquake.
What number do you think is more to get a higher magnitude, which you say that this is higher magnitude? Is it what number? Like what I'm teaching from that time is from 4 to 9. So what number do you think that makes it more shaky or which is destroying buildings? If you're listening to the class, you could have said me. Again, I repeat, we have magnitude 4, 5, 6, 7, 8, and 9. Listen to me carefully. In 4, you cannot even feel that there is an earthquake. In 5, the glasses will break. 6, they say the building on the epicenter might tilt or might fall. And 7, it will damage a lot. 8 and 9, it will destroy the whole city or the whole area with number of people dying inside that. So this is the magnitude numbers, girls, given. Earth magnitudes with higher magnitudes, earthquakes with higher magnitudes tend to cause more damage. Please, girls, science class, be active. What are you online for? Why are you sitting here? Just for me to speak and you all don't listen anything and then leave? What will you learn from this?
In 1985,
I'm showing you pictures so that, at least you look at them and try to listen them. Listen to this now.
In 1985, an earthquake with a magnitude of 8.1 occurred in Mexico. Many people were killed and many buildings collapsed in Mexico City. Mexico City is located on the loose sediment of an ancient lake basin. This geology increased the intensity of the earthquake. Seismic waves shook.
That's why they said that Mexico is a city which is located somewhere not in the good ground. That's why it was more prone to earthquake. Seismic waves, they shook the ground, which is made up of loose sediment saturated with water. The sedimentary rocks are very soft rocks. So that's why it's more prone to get an earthquake.
The ground, which is made up of loose sediment saturated with water, until it behaved like a liquid. The sediment behaved this way because the individual sediments became suspended in the water and could not come into contact. Buildings on rock tend to have less earthquake damage than those built on soil. Sand.
That's why the buildings which are built on rocks, they don't have much of chance to get damaged. Whereas the buildings which are on soil, to choose a good area is also very important. The one which is one which is built on soil, they have much damage of earth from earthquake.
The areas can develop scattered liquefied areas as small as a square meter. In this image, the sand liquefied under the house on the left, but not next door.
See, the next building doesn't get damaged, but this building gets because it is placed on soil. The greater the population in an area, the greater the damage. Of course, girls, when greater the population means the city has more buildings and more near things are placed, so that has more intensity of getting damage or more potential of getting damage.
An earthquake near a big city is likely to cause more damage than one in a less populated area because there are likely to be more structures nearby to damage. In remote areas, an earthquake may cause significant changes to Earth's surface without causing much damage to buildings and other structures. Engineers have found ways to design buildings to withstand the effects of earthquakes. Click the labels to learn about several features of earthquake-safe design.
Nowadays, especially in Japan, because they know from before that our land is more prone to earthquakes can happen here more. So while designing the buildings, the engineers are having special plans so that they make them fix in a way that it will cause less damage. I cannot say that it will not cause damage at all, but it will cause less damage. Let us click this.
As the ground shakes during an earthquake, the building is pushed and pulled in several directions. Cross braces counteract this movement, helping the building absorb energy and remain stable. Base isolators act like shock absorbers in a car. They are layers of rubber and steel between a building's foundation and the building itself. They are able to absorb some of the energy from the seismic waves, preventing the waves from traveling up through the building.
You know what? They said that we have something made up of steel here, and that is taking the shaking of the ground and not letting the building to shake a lot.
Mass dampers reduce the vibration of waves as the waves travel through a building. These dampers minimize the swaying in response to an earthquake.
So this base isolators and mass dampers, they are like holding the building and trying not to send the waves to all of the building, and they save the building.
If the water and gas pipes are not able to bend as the ground moves, they will break. Broken gas pipes could lead to fires and explosions. Flexible joints allow the pipes to bend without breaking. Some buildings are equipped with active tendon systems. When computerized sensors detect that a building is moving, the computer counteracts the movement by shifting a large weight. These systems can be used to prevent damage from high winds as well as from earthquakes.
Of course, it will be an expensive process, and not all of the buildings can, or not all of the companies can afford it, but still, it's very safe, especially in those areas where they know from before that this ground is prone to earthquake. Earthquake can occur there and damage a lot of buildings. So they can plan from before and get a better way to save their buildings. So that's it for today's class. And any questions?